Next, we'll hear from Olivier Vanakker, who's at the Ghent University Hospital. Olivier.
Okay, thank you very much, Sharon. And just try to share my screen. There it goes.
Yes, we can see your screen.
Okay, so good morning, good afternoon for everybody. In the next 10 minutes, I'll try to illustrate you how zebrafish can help to tackle ectopic mineralization. And I would like to start off with a very important disclaimer, which is that zebrafish do not equal humans, which means that everything that you will hear does not necessarily mean that it is immediately applicable in patients already. But it is a good start because although clearly a fish is not similar to humans to some extent, it is an interesting model because first of all, as you can see on this slide, there is what is called a high genome homology, which basically means that if you have an interesting gene in humans, that there is a good chance that a fish will also have the same gene to be studied. And it also has a similar development, which means that although they don't really look alike, fish and humans, that almost every organ and tissue that you want to study in humans is also present in fish. And they're really not that expensive, which is, of course, also an additional plus. So how does it work? Well, first of all, you start with creating a model. And as you can see here in this cartoon, it starts with very small fish embryos that are injected with this crazy tool that you can see, which is called CRISPR. And CRISPR basically is a scissor that will cut your DNA at a designated place. And in this case, it was used to cut the ABCC6 gene in a fish. And as you can see, there's something funny in fish with genes. They have 2 copies of each gene, which are coined A and B. But for this story, we'll just focus on the ABCC6A gene. The gene, as Koen already referred to, is the causal gene of PXE. And then, of course, the question is, do these fish have something that looks like PXE with the limitations of being a fish? And if you look at very young fish, and these are larvae of 10 days old, and you compare the normal one on the right to the PXE fish, you can see that the vertebral column is much more mineralized, it's much more red compared to the control. So they seem to have extensive mineralization. And if you look at older fish of 7 months, top one is the normal one, bottom one is the PXE fish. Again, you can see that in the spine, there is much more extensive ectopic mineralization leading to these deformities of these fish. So there is excessive mineralization, which is also the hallmark of PXE. So that's a good thing that the fish somehow resembles the human phenotype. So what can you do with them? I'm just going to focus on 2 main big topics, which is pathophysiological studies. So study the mechanisms leading to the disease, and then compound screening, evaluating drugs that might influence this mineralization. Because these are 2 of the main problems that we have currently in PXE. We don't know all the mechanisms leading to the disease, and we don't have a curative option that really targets the complete set of symptoms that, that patients are confronted with. And so the example that I would like to show you is, from a mechanistic point of view, is what we did around DNA damage. And DNA damage, basically, this is a very busy cartoon, but if you look at this DNA molecule, you see that what happens in DNA damage is that the DNA breaks in little pieces. And of course, nature will not tolerate that. Nature will do something, and basically there are 2 options. Either it will repair the damage, or it will have the cell die, so that the damage cannot do anything funny with your body. And to repair this, you get signaling, you get a set of activities that will lead to the repair of this DNA damage, and that is called DNA damage signaling. And as you can see, one of the side effects, if you follow these arrows, is that as a result of that, you get calcification. And one of the essential proteins is this one here, which is coined PARPs, which are basically the initial proteins that will set off this DNA damage signaling to correct the DNA damage. And if you study this in PXE patients, you will see that this DNA damage is much more active in patients compared to controls. And again, I'm just going to show you here on this graph, again, these PARP proteins. And if you look in PXE cells of the skin, you see these very thick bands in the patients. And these bands are also present in the controls, much less heavily. So there's much more of this protein available in the patients than in the controls, meaning that it is much more active. And also, if you look at the activity of the genes, for example, the PARP1 gene that produces this protein, you see that the activity is much higher in the black bar of the PXE patients compared to the controls. And also, every protein and gene that comes after this PARP1 in this signaling cascade is also higher, is also more active. And if you look at this in a fish, then you see that fortunately, it's exactly the same. In these fish, PXE fish, which is the gray bar, PARP1 is also higher compared to the control fish, which means that the similar mechanism that leads to calcification in PXE patients is also leading to the calcification in the fish. Which is interesting, at least this mechanism is interesting, because it's a mechanism that you can target with drugs which are called PARP inhibitors. Which brings me to the second part of what can you do with your fish, and that is to do compound screening. Test drugs to see whether these drugs have any effect on the mineralization. Of course, as a fish is not a human, at least you want to know if I do something with these fish and it has a positive reaction, will this have any success in humans? So you want to validate that the model, the zebrafish model, is a good first screening for drugs to be used later on in humans. And one way to do that is just take a couple of drugs that have already shown an effect in humans or in mice, for example, and then see what happens in zebrafish. And there are, of course, plenty of examples that have been used in the past, just as etidronate, alendronate, vitamin K, sodium thiosulfate, magnesium, which have, to some extent, an effect on the calcification in PXE. And if you test these in the zebrafish, and I'm just going to show you the result for etidronate, if you treat PXE zebrafish with etidronate, you get the following results. So this is the untreated PXE fish. This is the treated PXE fish. And as you can see, the mineralization in the spine is lower in the one that is treated with etidronate compared to the untreated one. So this means that this zebrafish can be used as a screening tool to select certain drugs, new drugs or compounds that can be then further investigated with other experiments. But at least to select, to have a first selection, this tool seems to be efficient. Coming back to our DNA damage, as I said, you can target this signaling pathway with drugs that are called PARP inhibitors. And the one that is best known is minocycline, which is already used in clinic. PARP inhibitors are used, for example, in cancer treatments. So they are used in a very frail patients, and because they don't have that many side effects. And if you use this minocycline, this PARP inhibitor, in a zebrafish, in the PXE zebrafish, then you see here in the middle an untreated PXE zebrafish, below a treated PXE zebrafish. And as you can see, the treated one has less calcification compared to the untreated one. So a PARP inhibitor does seem to help in reducing the calcification in this PXE model. And this puts these in creating a drug that can be used in clinical trials, that puts the zebrafish at the very beginning, where you will select from a large number of drugs, you will select those that seem to be interesting, that seem to have an effect on the calcification, and those are called then the lead compounds, the ones that you will study further in other experiments. And the next step, of course, is a mouse model to be used. And just to illustrate, for minocycline, we have done this last year. And there, if you look at the PXE knockout mouse and you look at the calcification in the whiskers, which is the biomarker for PXE, you see that the treated mice have less calcification in their whiskers compared to the untreated ones. So again, also in mice, this minocycline seems to be helpful in reducing the calcification. You can also see that in the scans shown below. So for translational research using zebrafish, you first create a model, which we did with CRISPR, to knock out the gene of interest, and then you can use it to look for and study mechanisms that lead to the calcification in different model organisms. You validate it for compound screening just to make sure that whatever comes out of a zebrafish at least has a chance of also working in mice and in humans, which does not mean that that will always be the case. But in this case, for at least PARP inhibitors like minocycline, we have come that for the most powerful one, we show that it works in zebrafish and also in mice. And it still has to be refined, but might be in the future a potential interesting candidate for a clinical trial. And with that, I will thank you for your very kind attention. And of course, if there are questions, I'll be happy to answer them.
Wonderful. Thank you, Olivier. Questions? Okay, so the first one is, what are the next steps post zebrafish and mice? Are you going to move to humans, and what will your timescale look like?
Yeah, so the next step is indeed to move to humans. There is basically nothing after the mice, but there are different PARP inhibitors. So minocycline is the one that is most powerful, but is also the one that if you use it, for example, if you have to use it daily, monthly, that it might have some issues with how you will provide it to the patients. But there are several others that are very similar and that we are testing now just to find out if they are equally good as what we see in minocycline. And those might be easier from a practical point of view to use as a treatment. So we hope to have results of that in the next up to 6 to 12 months. And then it's just a question of indeed getting ethical approval and see if we can start off with a clinical trial if, and that is an important if we have a good biomarker for PXE. Because I think that is the problem at the moment with every clinical trial, even with the drugs that are ready to use at this moment. And that is, how are we going to know on short term, and that means 2, 3, up to 5 years, how are we going to know really that the drug is directing PXE in the right direction, that it is actually doing something, and that the drug has a positive effect. And I think that is the big challenge that we are all facing right now, is to come up with a reliable, easy to use, validated biomarker that can really tell us whether any drug that we would like to test is going to be the right one for PXE.
Great. Thanks, Olivier. That's part of what we talked about yesterday for sure, is that one of the good things about PXE, when you live with it, it's very slow. It's very variable in the sense that you're not destined in any sense to have one or another of the various symptoms, but it also makes it very hard, unlike a condition like progeria or ectodermal dysplasia or some of the conditions that are very quick to wreak havoc on the body. And the other thing that you mentioned that I think is really critical is any of these drugs will have to be taken for a very long time, and probably started at a young age to be given prior to any damage. And so there's a lot of considerations about taking something for a very long time when in other conditions, like the PARP inhibitors, it's for a shorter time. So there's a lot of challenges with that as well. Okay,
Absolutely.
thank you very much for giving us part of your Sunday,
No problem.
and for your work. Thank you.